Hello and welcome to Team 563-1's final presentation on our final robotic marker holder. This presentation was created by undergraduate engineers, myself, Suriana Lee, Kevin Ho, Leila Idrissi, Grace Shenefelt, and Jonathon Sonneborn. Robot art is a type of kinetic art that uses robotics and automated technology. This can be traced back to the 1960s and is an up-and-coming industry in the modern day. For this project, the problem we are trying to solve is to complete an autonomous robotic drawing. We are tasked with designing and 3D printing a dual marker holder and programming the robot to create this drawing. The purpose of this presentation is to display the results of the final project and discuss societal impacts of robotic painting. The agenda for this presentation is as follows. First, we will watch the videos of our final product. Then we will discuss our vision for the marker holder, in which we brainstormed and CAD modeled our marker holders. Then we will go over the AM processes, in which we 3D printed the marker holder. Next, we will discuss RobotStudio, in which we will show a brief simulation of our toolpath. Next, we will discuss what we learned from the design process. Then we will discuss the societal impact of robotic painting. And finally, we will wrap things up with a conclusion. Now we will watch videos of our final robot drawing. This is the final drawing of our striped engineering block M. As you can see, the letters in the word engineering did not print out correctly, so we had to trace over the outline a second time. After we traced the outline, we flipped the robot's 6-axis 180 degrees in order to draw the inner stripes in yellow. Now I will pass it off to Leila to discuss our vision.
Thank you, Suri. We created a T-shaped design for our marker holder. As you can see, each of the markers are placed into their corresponding arms facing outwards. Our design allows the ABB robot to switch colors easily by rotating the tool pen 180 degrees. Our holder also allows flexibility by securing springs that absorb the pushback force of the marker. For our CAD model, we use steps that involved extruding, mirroring, creating an offset plane, mating, and assembling. This is our final marker holder fully assembled. This is our final drawing. And here are some visuals of the marker holder attached to the robot. Now I will talk about the AM processes we completed to fabricate our marker holder. We first uploaded an STL file of our CAD to Cura. The images on the right show the Cura slicing towards the beginning and ends of the print. We used a printer core of AA 0.4 and an infill of 20% with the triangle pattern. Our printing temperature was 205 degrees Celsius and our bed temperature was 70 degrees Celsius. Finally, our print speed was set to 70 millimeters per second. We 3D printed our holder using Ultimaker 3 printers at the Duderstadt Fabrication Studio. We used PLA material for both the print and the supports. It took a total of 3 attempts to print our marker holder. The first attempt did not fit the markers correctly, and the second attempt had poor adhesion to the bed. All the prints had around a 2-hour print time and up to a 1-hour support removal process. The total AM process for including all the attempts took around 8 hours. Finally, we had to widen the set screw hole using a drill and used an Allen wrench to place the set screw in the hole. Now our marker holder is attached to the flange adapter. Then we place the marker holder and flange adapter on the robot using a ratchet. Now I'll be passing it off to John, who will talk about the programming of the robot and running the simulation in RobotStudio.
Thanks, Leila. In the RobotStudio software, we program the toolpath of the robot in order to move the marker to various points on the whiteboard. Using these points, we were able to get the robot to draw our design. The image to the left shows the toolpath used by the robot, with the blue lines representing the path that the blue marker used, and the yellow lines representing the path that the yellow marker used. The image to the right shows the ABB IRB 140 robot arm with our 3D modeled marker holder attached to it in the RobotStudio software. And now I'll show you a video of our simulation running the toolpath. And now I'll pass it off to Kevin Ho, where he will talk about what we learned from the design process.
Thank you, Jonathan. Now I'm going to discuss the issues we encountered during the assembly and simulation of our design. Then I will discuss future improvements we can make to our pen holder. One of the first problems we had was with the predicted error of our drawing. This was because the first time we calibrated the robot, we failed to do it accurately enough. To calibrate the robot, we had to touch the tip of each marker at 3 different orientations to the calibration needle. To do this, we used linear movements as well as rotations of the 4th, 5th, and 6th axes to move the robot into the desired positioning. Unfortunately, we had to recalibrate multiple times because there was too high of a predicted error in the accuracy of the point. Eventually, after recalibrating many times, we managed to get the error small enough that we could neglect it. The next issue occurred after we had updated our P10 and P20 and were ready to start the program. The robot ran through our programming, but part of the word engineering in the drawing was not drawn completely. This was because the writing surface was on a slight incline. To fix this, we lowered the point at which the marker touched the bed, and after running the program again, it turned out as intended. After our first run through, we decided to make some adjustments to our code. We think that one of our issues with our program was that P10 was overwriting itself in the second program. It was in a slightly different location when we switched to the other side of our pen holder due to it not being perfectly made and assembled. Thus, we made P20 our safety position and P10 the point touching the bed in the first program. We then set P30 as the point touching the bed in the second program with the yellow marker and updated the safety position line, also adding a copy of it to the end to ensure that the robot would return to that point at the conclusion of the program. We hope that this would make our drawing more precise and accurate. Finally, the stripes of the first drawing came out green since the yellow and blue markers blended. We hoped that drawing the yellow stripes first would solve this problem. We were correct, since there was no color blending in our final drawing. However, our final drawing came out unclear since the marker was pushing down on the surface too hard. This caused the writing to be unsteady and thick, which made the letters blend together, and there were obvious points at which the robot started and stopped. This likely was caused by an excessive amount of torque on the marker, causing the lines to not appear straight. Here was an image of our final drawing with shaky writing. It is especially obvious in parts of the block M and some of the letters that the robot and the marker were shaking. To solve this, we brainstormed some ways we could have improved our design to make the drawing less shaky. We decided that we could decrease the movement of the marker if we increase the length of the holder and decrease the size of the holder opening. This would give the marker a snug fit that would ensure any movement of the marker is due to the robot alone. Now, I'm going to briefly discuss our Gantt chart. Some of the key dates for our final project were visiting the fabrication studio on March 24th to print our 3D marker holder, testing the holder on the robot on March 31st, and of course, our final lab to run the code and draw our design on April 12th. Between these dates, we worked on other components of the project that would ultimately lead to our final product. Almost always, we were on or ahead of schedule to finish the project, and in the end, we completed it on time. Thank you. Now I'm going to turn it over to Grace, who will discuss the social impact of robotic painting.
Thank you, Kevin. I will now discuss the societal impact we decided to look into further, which is the population of art consumers. We anticipated that the population of art consumers would increase. This would be because the increase in accessibility to robotic art would mean that more people are now able to create art. Specifically, those with disabilities or chronic illnesses that prevented them from doing art before can now participate. It would also result in a decrease in cost because robots would be able to mass produce art, whereas humans have much more difficulty doing that. And a decrease in cost would lead to an increase in demand. We also believe that new customers would be attracted to the market. Here is the outline of our societal impact study. First, our population would consist of anyone who can buy art. We were going to ask, does increased availability of robotic painting widen the number of people who buy art? We think that an increase in robotic painting availability will increase the number of people who purchase art. To test this hypothesis, we will conduct a mixed method study by conducting surveys and focus groups. This will allow us to gain qualitative and quantitative data. Here are the studies we will conduct. The first thing is a national survey for 5 years in a row, which is a repeated cross-sectional study. These participants will be asked a series of close-ended questions, including asking whether they prefer robotic or human painting, and also asking them the number of paintings they bought in the last year, and if those paintings were made by robots. Then we will conduct a focus group on the 1st and 5th year that we conduct the survey, and we will ask the participants open-ended questions and have real-life conversations with them. We will also ask them if they prefer robotic or human paintings, and we will ask them their reasons for currently buying or not buying art, and what would make them more likely to buy art in the future. Now we will wrap it up with our conclusions. First, the importance of learning industrial robot programming. We were able to learn all about programming with the Flex Pendant and RobotStudio, which was really a great experience, and we learned a lot. We learned about plotting points in space and how the robot's 6 axes manipulate the points and interact with them. We also gained a great understanding of the 3D printing process and learned a lot of problem-solving skills, which is crucial for any engineer. The things we enjoyed most were getting to experience the entire design process. We really loved the 3D printing especially, and going to the fabrication studio because we loved seeing our CAD model come to life. We also really enjoyed controlling and programming the robot and getting the hands-on experience that is so crucial to engineering. Along with that, just having the ability to have an in-person lab was really nice because most of our other classes were completely online, so it gave us the chance to interact with our classmates in person and also get the hands-on experience. Lastly, the summary of our project. We successfully designed and created our marker holder, programmed the ABB IRB 140 robot, used our holder and code to make our drawing, learned a lot, and had fun along the way. Thank you for listening to our presentation, and we want to give a special thank you to all our professors who put in countless hours of work, and we love this class. So thank you very much.
Thank you, Grace. This concludes our presentation. Thanks for listening, and we will now take any questions.